Hello and welcome back to this NPTEL course on advanced plasticity of solid continua. So, we were discussing so far the various aspects of rate dependent plasticity, especially the Perzyna type model, but without accounting for heat transfer. That is precisely what we are going to start today. The problem will still be rate dependent, plasticity of the rate dependent type, specifically of the Perzyna type, but accounting for the thermal effects. All right. So, let us get going. So basically let us continue to consider the Perzyna model, but with heat transfer. Perzyna model, you remember, is that particular plasticity rate dependent model in which there is a rate independent part in the dissipation functional, right. So, Perzyna model accounts for a rate independent component even though the overall problem is rate dependent, right. So, there is the notion of this yield surface that comes in, even though the forces, that is the stresses, are not restricted within the yield set, it can go past it, that is called the overstress, if you remember. So, the use of the convex analytic framework has served us well so far. That is what I think you will agree with me, having come with me to this part of the course, that our convex analytic framework has helped us pose the elasticity plasticity problems within the same optimization framework by just changing the functional which we minimize. So, to continue with our convex analytic framework, we have to transition from a purely mechanical potential that we have so far been using to a thermodynamic potential which is also temperature dependent. Okay. So, the free energy has to be temperature dependent, and the dissipation potential also can be temperature dependent. The thermodynamic state functions, the state functions which are basically actual states in the thermodynamics are the total strain, the absolute temperature theta, okay, and the internal variables alpha. Now, if you recall, these internal variables alpha contain both the plastic strain and the hardening variables, okay. So, all of these are included in alpha. Let us now move on. Remember that we are talking about rate dependent plasticity with heat transfer. So, we need to see how we are going to split our energy. Energy, physicists and mechanicians often have the habit of splitting energy additively, right. So, if there are multiple effects, put each effect in each one of these components in the additive decomposition, right. So, here we do the same thing. So, this additive decomposition of the free energy, one part is the purely elastic part, the second part is due to the plastic flow, okay. The third part is because of the thermal part, that is due to heat transfer, which is a function of only the absolute temperature. The first part is obviously a function of the elastic strain. Now, unlike the last cases where there was no heat transfer, now the elastic strain will have to be found by subtracting from the overall strain both the plastic part as well as the thermal part, okay, right. So, it is the Thermo-visco-plasticity problem, right. And then psi p, which is the plastic part of the free energy. Why plastic part of the free energy? Because we have hardening variables, right. These hardening variables can actually store energy, even though only pure plasticity, like perfect plasticity, does not store any energy in psi, but in hardening plasticity we have this case, we have discussed this earlier. So, that is why this, and there is a third part, possible storage of energy because of temperature alone. Why? Temperature can actually cause microstructural changes on its own, right. This is because of thermal activation. So, it is quite understandable that there should be a part of psi which should be a function of theta, okay. So, the thermal part of the strain epsilon theta h is given by alpha L, that is the coefficient of thermal expansion alpha L, times the temperature difference from a reference theta 0, theta minus theta 0 is the temperature difference, that is the actual value times I is the tensor, identity tensor. So, that is the standard thermal part of the strain. Okay. So, alpha L is the coefficient of thermal expansion. So, psi E is the elastic stored energy, psi P is the energy stored due to the cold work. So, this hardening is a microstructural change of a very specific kind, because of which the work is stored in psi, and this is called cold work. Okay. This is the typical term used. This is to say that this happens, the work happens without a specific input of temperature, right. Even without temperature you actually do work purely based on the these alphas. Okay. So, psi theta is the thermal contribution, right, it is related to the heat capacity. So, the constitutive relations, now let us talk about them. So, the constitutive relations will have to be found based on the Coleman-Noll procedure, as exactly as we have been doing for quite a long time, right. So, leading to thermodynamic closure. So, for that you use the local form of these the combined dissipation inequality, which is given here, that is combining the two laws, okay, also called the Clausius-Duhem inequality. That is, the dissipation is given by, this is one term which is related to the the stress power, it is called, remember, sigma inner product with epsilon dot minus the rate of psi plus eta theta dot, okay, minus q is the heat flux dot product with there is a dot product in between delta theta, the nabla of theta, that is basically the gradient of theta. Okay, q is the heat flux and theta is the temperature. Okay, this is greater than or equal to 0. You remember this form. If you do not, please flip back, stop this lecture for the time being, flip back to those portions where we discussed this by combining the two laws, and make yourself comfortable with this form of the dissipation inequality. Okay. So, D here denotes the dissipation, basically a dissipation density per unit point, for every point wise, per unit volume. So, psi now is a function of epsilon, okay, alpha and theta, all right. So, therefore, I can use this standard expansion based on calculus of psi dot, which is equal to del psi by del epsilon inner product with epsilon dot, plus the other terms del psi by del theta theta dot plus del psi by del alpha alpha dot, all right. You remember these things, and then substitute this psi dot back in the expression for the dissipation, and then put the terms properly. This is the Coleman-Noll procedure, that is what we are doing, right. So, put the terms properly such that the factors of epsilon dot, theta dot, alpha dot, etc. become clear. Okay. So, this is the factor of epsilon dot, this is the factor of theta dot, forget about the other things. Now, the point is that, recall, based on Coleman-Noll hypothesis and the way that we proved things, at that time we proved it also, that epsilon and epsilon dot and theta dot can be chosen independently of each other, okay, based on locally, of course, purely based on tangent space based logic that we have proffered when we discussed Coleman-Noll. If you have forgotten it, my suggestion will be for you to go back to that lecture and go through it once more, okay. Otherwise, some connections will be missed and you won't enjoy the entire process that much. So, our closure relationship therefore means becomes sigma equals del psi by del epsilon, because this has to go to 0 for this to be greater than 0 or equal to 0, right, for this entire expression to be non-negative. Similarly, this also has to go to 0, that means eta will be equal to minus del psi by del theta. These are the standard things which we derived earlier also. The interesting thing here is that it is still coming up even in this case, okay. So, there is some universality in this, irrespective of the problem that you were solving, we always see that sigma equal to del psi by del epsilon or eta equal to minus del psi by del theta, these expressions are always valid. then if these are the cases, then we see that these expressions, these first two terms in the expression for the dissipation does not create any dissipation per se, because these are all zeros, right. So, the other two terms must be creating some dissipation. So, therefore, we can write the reduced dissipation inequality by removing them, the first two terms, and retaining the rest, which is here, minus del psi by del alpha alpha dot minus q dot grad theta divided by theta. Okay. Now, you can define this is conjugate to alpha dot, right. So, you can think of this to be as kind of a force like object, thermodynamic force, and call this by x. So, x is minus del psi by del alpha. Acting on alpha dot, this x creates power, okay, which is dissipated. Basically, we can actually write this way, and then we can write this psi dot in terms of sigma epsilon dot minus. So, basically you see that psi dot, there were three terms. One was del psi by del epsilon, which is sigma here. So, sigma epsilon dot, right. Del psi by del theta is minus eta. So, minus eta theta dot, like that, and del psi by del alpha is minus x, right. So, this is all that we are using here, and we get this psi dot equals this, okay. So, this part is also should be clear to you, all right. Okay, so we will be using this identity for psi dot shortly. It is very useful for us. I will tell you why. Now, there is something here. So, psi typically you have known about it, right. We have been using this fact that psi is a convex function of all the arguments. That is no more true. Psi is not convex in theta. Psi is actually concave in theta, that you must understand. Why is it? If it is not true, if psi is made convex in theta, then heat will flow from regions of low temperature to higher temperature. That is not how it happens, no. Heat flows from regions of high temperature to low temperature, right. So, it flows in the negative direction of the gradient of theta to account for that, but I will come to this. So, recall the thermodynamic definition of specific heat at constant volume. Okay, that definition gives you the specific heat at constant volume and strain. A constant volume is given by theta del eta by del theta when you hold epsilon, that is the strain, and alpha fixed. How did we get there? Let us say q is the heat, okay. So, you know that q is not a state function, because q is a quantity that gets dissipated. So, it is not conserved. So, therefore, when we say incremental heat, q is the heat. If we say incremental heat, if you integrate this over a closed loop, you should get 0, right. But that is not the case, because by the time, suppose you are actually integrating this quantity over a closed loop q, right. So, you have starting q from here, then going this way, this way, this way, but by the time you come back here, the same point, some heat would have got dissipated. So, integral dq over a closed loop is not 0. So, therefore, q does not, the increments of q does not satisfy the standard rules of calculus, right. So, we call this increment by something like this inaccurate dq, something like that. Okay, that is actually so how is entropy defined? So, if you call eta to be the entropy, then entropy is basically dq by theta is the entropy, the usual definition of entropy, okay. Theta is the absolute temperature. On the other hand, the definition of CV is that CV is the heat needed to increase the temperature by unity. That means CV dt, d theta I am sorry, must be equal to this dq, right, locally, is not it. So, if you actually now combine these two, or rather use instead of this dq this, then you get exactly what actually I have written here, theta delta eta by delta theta, okay. So, but we already know from the closure that eta is actually minus del psi by del theta. We have already seen this, right. So, if you put this, then we see that CV is minus theta del square psi by del theta square, but CV has to be greater than 0, because if you put some heat, you expect the temperature to rise, no, at least it should not reduce. If you put some heat, temperature should not reduce, right. So, CV has to be greater than 0. That means given that theta is positive, del square psi by del theta square must be less than 0. That means psi has to be concave in theta. You understand? So, psi is as such convex in the other quantities on which it is dependent, that is strain and also the alpha, but psi is definitely concave in theta. This you must keep in mind. Okay. Now, so this is basically what we have said here. Theta is strictly positive, so therefore del square psi by del theta square from the definition of CV is less than 0. So, this is concavity of psi in theta. Our objective now is to derive a generalized heat equation for this theta. Okay. The reason I am actually spending some time in explaining to you this generalized heat equation is that this gives a lot of physical understanding of how plasticity works and how the dissipation occurs, right. The generalized heat equation that I will be deriving now is not needed as part of the solution scheme that we are talking of. That heat equation will be a complicated PDE, partial differential equation, but it will be anyway solved. The incremental temperature will be solved based on the minimization of some functionals, right, in our scheme by the convex analysis. So, what we are saying is that it is practically not useful for us in solving the problem, but it gives a lot of interesting insight. So, you know about the usual heat equation, right. The usual heat equation, for example, del theta by del T is the conductivity, correct, you know, the Laplacian of theta, that is the standard equation for heat. The effect of this Laplacian of theta you understand, right. So, the second order derivative of theta with respect to this appropriately, you know. So, with respect to the spatial coordinates. The point I am trying to say is that this is also called the diffusion term, right, diffusion. There is a reason for this, because the heat diffuses, right. So, if you actually have a very high temperature at a point in a solid body, slowly after some time the heat will diffuse, and therefore the temperature at that point will go down and the temperature elsewhere will go up, right, until the point the temperature everywhere remains the same and is equilibrated with the surrounding, the ambient temperature, right. Till that happens, this process will continue. This equation is exactly a representation of that. It is exactly the same thing as saying that if you have a bucket of water, you put a drop of, you know, ink. So, until and unless you see the water to be getting uniformly blue, let us say the ink is blue, to be having a uniform color of blue due to the diffusion of this drop of ink, this process continues. Finally, you will see the water to be uniformly blue, then it is stopped, okay, but that is at infinite time. So, this is the example, this is the mathematical description for that same process. Anyway, so how the question now is this heat equation, how is it modified, right, because of plasticity. So, in order to understand this generalized heat equation, recall that we have the free energy psi defined in terms of the specific internal, in this case specific, that word is not important because there is only one configuration. So, multiplying any energy like quantity by rho, the mass density is not very useful because we are not using these transport theorems here. We can directly take the derivatives inside the integral because the integrals are always over the body domain which is fixed here. Okay. So, this is the the internal energy E, and theta is the temperature, eta is the entropy. Alright. So, if you differentiate this and rearrange, then you have E dot equals psi dot plus theta eta dot plus theta dot eta, alright. So, now let us now invoke the first law of thermodynamics. We have one expression for E dot from here, which is basically from the definition of free energy, okay, you know, as E minus theta eta. It turns out that this definition of free energy is related to the legend of Fenchel transform that we have been talking of, but I am not going into that details now. It is not very important in this context. Right. So, this is one expression for E dot. Another expression for E dot we have from the first law of thermodynamics, if you recall, and that expression is here. This is an alternative expression, right. So, this expression tells you that E dot equals sigma inner product with epsilon dot minus the divergence of the flux plus this R is the source, right, heat source. So, in typical cases often you typically set R equal to 0, but it does not matter. So, we have two different representations for E dot, we can equate them. Once you do this and do a little bit of algebra, then you get this generalized heat equation basically, you know. This algebra we will come to, but the basic idea is just this, right. So, now let us do this exercise now one after. So, once that we know that the basic idea is to equate these two to get the heat equation after some algebra, let us concentrate on the algebra now, right. So, use E dot equal to this from here, okay, in this E dot, okay. So, then we have got this straightforward identity first, okay. So, no issue so far. Next, let us use the previous expression for, you know, we actually got this expression for psi dot, you remember, just some time back. We used psi as a function of alpha, epsilon and theta, and then did psi dot the expansion in terms of this, and used Coleman-Noll closure, okay, to actually arrive at this some time back, just some time back. Now, if you are not comfortable, then flip back to that page and make sure that you understand this step, okay. So, let us use psi dot as given here in the identity, the first of these two identities for E dot, okay, which is the first of these is E dot equal to psi dot plus theta eta dot plus theta dot eta. Put that. So, we get this, okay, straightforward so far. All the steps are straightforward here, there is no issue. Now, you see that certain terms will cancel, only I think this term will cancel, you know, this term will cancel with this, correct. So, you know, you have this rest of the terms here, okay. But you know, from the first law we have an additional expression for E dot that we already seen, right. So, now you equate this form of E dot with the first law's form of E dot, okay. So, then you have instead of E dot the right hand side of the first law, which is this, equals the right hand side of this identity, which is this. So far it should be again clear, right, these algebraic steps, the manipulations, that is all. Now, if you simplify this last relation, because you see that this will cancel, okay, and then you know, you just, you know, properly write it. So, theta eta dot you write on the left hand side and the rest you push to the right hand, then you have this, okay. Now, take the functional dependence of eta now. It should depend on similar variables as psi dependent, okay. So, eta should depend on the strain epsilon, eta should entropy, right, it should depend on the alpha, the you know, the other variables which are responsible for plasticity, the internal variables, and it should depend explicitly also on temperature. So, if you actually account for this, then eta dot is exactly of the same form for based on which we wrote psi dot, okay. So, delta eta by delta epsilon inner product with epsilon dot and etc., delta eta by delta theta, etc., okay. Now you see that eta is already minus del psi by del theta from the Coleman-Noll thermodynamic closure. So, whenever we are getting the first derivatives of eta here, del eta by del epsilon etc., we see that we are getting second derivatives of psi in the process, right. Let us now use the symmetry of this second derivative, because psi is smooth. So, I can use the symmetry, that means the order in which we take the derivative does not matter, right. If we use that, then we arrive at a sequence of very interesting relations which Maxwell in Edinburgh derived about more than 150 years ago, right. These are called Maxwell's relations. Okay. These are very standard things in thermodynamics, but I am just making them explicit here, right. So, the first thing that we need is delta eta by delta epsilon, right. So, that delta eta by delta epsilon is delta epsilon of minus eta is minus del psi by del theta. So, now you flip the derivatives. So, del psi by del epsilon with a minus sign gives you minus sigma, right, sigma. So, derivative of sigma with respect to theta, right. You see del psi by del epsilon is sigma, that is a standard closure relation. So, this is one of these Maxwell's identity, very important identity, I mean. Then we have delta eta by delta alpha, okay. That you actually write as again in the same way, eta replaced by minus del psi by del theta, and then flip the swap the derivatives. So, this will be minus minus del psi by del alpha, that is the first derivative, and then you take the derivative with respect to theta. Okay, but minus del psi by del alpha gives you x, the thermodynamic force conjugate to the flux which is alpha dot, you remember x is minus del psi by del alpha. So, use that x to write this whole thing as del x by del theta. Okay. Similarly, finally, from the very definition of the specific heat Cv at constant volume, we have this relationship. That is the definition of Cv, which we proved some time back, okay, I mean which we showed to be valid some time back. So, if you substitute these Maxwell's relations in the expression for eta dot based on the functional dependence of eta on quantities like epsilon, alpha and theta, correct, then you get this. Okay. So, then what we need to have is basically we have this this theta eta dot equals this, all right. So, but remember that some time back we already had an alternative expression for theta eta dot, right, which we got some time back. You may have already forgotten it, I hope you have not. That was the expression. So, again we can equate the two, right. So, that is what we will be doing to derive the full form of the generalized heat equation, but we will actually stop here because already we have been talking of lots of identities and lots of different types of logic, including of course one thing that you may not have heard so far, that is the inexact differential of Q and things like that. So, I will give you a little bit of time to digest these things, and then before we come back to the next lecture, we will start the next lecture by actually based on this logic straight away now deriving the generalized heat equation, and then we will try to understand what kind of insight this generalized heat equation provides us with. Okay. All that are coming up in the next lecture. Till then, goodbye.